In this video, I'd like to spend a moment and discuss what vectors are and how they are represented in 2D Cartesian space. Vectors are a collection of things. In mathematics, they're a collection of pretty much any mathematical entity. As an example from programming, the C++ standard template library includes a vector container, which is a container for values of any particular data type. So vectors are just a collection of things. But this definition of a vector is quite vague, and whilst vectors can hold a variety of different items, when talking about vectors in computer graphics and programming, we're most commonly referring to something quite specific, a collection of numbers. But what is a number? Well, when talking about vectors, a single numerical value that we generally just call a number is actually referred to by a different name. It's called a scalar, which is spelt S-C-A-L-A-R. So it's a scalar, but this is just simply a fancy name for a number, a single value. But what can this value represent? Well, a single scalar, a single number, can represent only the size of something. It's a magnitude. How large is some quantity? For example, how fast are we travelling? 20 miles an hour. A single number, 20. How heavy is this object? 50 kilograms. A single number, 50. How much energy is this light bulb emitting? 100 watts. A single number, 100. So why would we wish to collect these scalars together? What possible uses could we have for a collection of numbers? Well, the classic example is that of the difference between speed and velocity. Speed is just a scalar, it's a magnitude. How fast are we travelling? To use our earlier example, let's say we were travelling at 20 miles an hour. So speed is a scalar, for example, 20 miles an hour. But velocity, on the other hand, is a vector. It tells us more than just speed because it combines speed with some other piece of information. It actually combines speed and direction. So if our speed is 20 miles an hour, we actually have an infinitely large range of possibilities for what our velocity could be. For example, if our speed is 20 miles an hour, perhaps our velocity is 20 miles per hour north. Or perhaps it's 20 miles per hour east, or perhaps it's 20 miles per hour northeast. We simply don't know unless we specify in our velocity the direction. So by combining speed and direction, velocity tells us a lot more than speed alone. So speed is a scalar, velocity is a vector, and it tells us speed and direction, and that's very important. It's combining multiple pieces of information together to tell us how they relate to each other. We're not just dealing with speed, and we're not just dealing with direction, we're dealing with speed in a given direction, and that's very, very useful. For example, let's say that we had a boat that was sailing at 20 miles per hour and there's a wind of 20 miles an hour. So we're just dealing with the speed of the boat and the speed of the wind. We have no idea whatsoever what effect that wind might have on the boat. Will it speed it up? Will it slow it down? Will it take it off course? We simply don't know. It all depends on how that wind relates to our boat's heading. However, instead of representing our boat's speed, if we talked about the boat's velocity, and instead of talking about the speed of the wind, if we talked about the velocity of the wind, we'd know a lot more about the situation at hand. So if we said the boat was travelling 20 miles an hour north, we know the direction and the speed that the boat is travelling in. If we then said that our wind was blowing 20 miles an hour south, that tells us a lot more about the effect of the wind on the boat. We know it's going to be blowing against our direction of travel, against the direction in which our boat is travelling in. And because of that, we know it's going to be blowing against the boat, making the boat have to work harder. It would be applying some force to our boat that would slow it down. Alternatively, if the wind was blowing 20 miles an hour north, we know it would be blowing in the same direction of travel as our boat. So it would apply some force that would help speed our boat up. Another alternative is that our wind was blowing 20 miles per hour east. It would be having a much bigger impact on our boat in this case, because more than just slowing it down or speeding it up, it would be applying a force that could cause our boat to go off course, because it's applying a sideways force, sideways to the direction of travel of the boat. And the only reason we know all of this is because we know the speed and the direction, and that means we know a lot more about the scenario we're dealing with. So velocity, being a vector, is far more useful to us than speed alone, because speed is just a scalar. But we said a vector is a collection of items, if you will, and we said that more commonly the vectors that we're dealing with are a collection of numbers. So how can we write velocity as a collection of numbers? We're all familiar with how we can write speed as a number, but how can we write velocity as a collection of numbers? Well, so far we've discussed the magnitude, which is our speed, and we know that we not only have a magnitude, but we have a direction as well. So speed is a number, our magnitude is a number, but how can we represent direction as a number? Well, one example, and this is not the way that vectors are usually represented, so don't worry too much about where I'm going. I just want to sort of have a little bit of fun and develop this in logical steps, if you will. One example is a bearing, an angle of rotation, if you will. So we could have north, south, east and west, for those of you who are familiar with a compass. And we know that as we rotate around in an anti-clockwise direction from north, we have a bearing that goes from 0 to 360 degrees. So if we had some direction we're travelling in, we could represent that as the angle, as the bearing, and we also then know the speed that we're travelling in that direction. We could take our bearing, which is a number, and we could take our speed, which is also a number, collect them together, we'd have a vector. It's a collection of two numbers. But this, you know, is a little bit like a point on a circle. In Volume 1 and Volume 2, we discussed circles in quite some depth, and we saw if we had a circle, now please forgive my drawing skills here, but if we had a circle, we know that a point on that circle can be represented by knowing the radius of the circle and the rotation from the x-axis. This is almost the same scenario. We've almost got some rotation and a length of our vector, or some rotation and the radius of our circle. And if we think about representing a point on our circle in this way as a rotation and a radius, this actually gives us something quite a bit like the idea of spherical coordinates. Now, spherical coordinates, we don't need to go into them in detail here, they're not really appropriate, but for those of you who are interested, spherical coordinates are a way that we can define a point on a sphere by using two angles of rotation and a radius value. Only here we're dealing with a circle and we're dealing with it in 2D. Now, we did discuss back in Volume 1 what the most common coordinate system in computer graphics and programming is. And we didn't say that it was the spherical coordinate system. If you recall, the most common coordinate system is the Cartesian coordinate system. So perhaps using an angle, a bearing if you will, and a speed is not the best way of representing our vector, because this doesn't exactly relate to our Cartesian coordinate system. It's dealing with spherical, or I guess you could say circular, coordinates. So how can we represent our vector using the Cartesian coordinate system? Since if this is the most common coordinate system, the coordinate system that we're going to frequently be working in, it makes sense to represent our vectors in that system. Well, we know the 2D Cartesian coordinate system consists of two axes, an x-axis and a y-axis. So what if we represented our speed and direction in 2D space by thinking of breaking our velocity down into how far are we travelling in x and how far are we travelling in y? For example, if we were travelling 20 miles an hour in the direction of x, so for example, if we were travelling 20 miles an hour in the direction of x, then we'd know that we'd be travelling 20 in x, 20 miles an hour in x, and nothing in y. So we'd have a vector that could look something like this. If this was our vector and it was 20 units long, we know that we'd be travelling 20 in x and nothing in y. But for example, if we were travelling at 45 degrees, something like this, again 20 units long, so we're travelling at 20 miles an hour in this direction, well, we could break this down into how far have we travelled in x, and then how far are we travelling in y, or in other words, how fast, because we're dealing with a velocity, how fast are we travelling in x, how fast are we travelling in y, and we could actually apply Pythagoras' theorem here and work out it's about 14 units in both x and y if this was an angle of 45 degrees, but that's sort of getting away from the point here. The point is that we can represent this particular direction and speed by saying how fast in x, how fast in y. So our speed is the magnitude of the velocity, it's how fast, and in terms of the resultant vector, it's represented by the length of that vector. The direction of our velocity is simply given by the direction of that line. So we can represent our vector in terms of its movement in x and its movement in y, if you will. It's almost like a pair of coordinates, an x value, how fast are we travelling in x, and a y value, how fast are we travelling in y. So we could actually write this as something like the following. We could say our vector is equal to some value in x and some value in y. It's still a collection of numbers, it's still a vector. The two numbers here, however, are telling us how our vector relates to x and how our vector relates to y. Now the first thing you'll notice with how I've written this is that we can assign a vector to a variable, much like we can assign a scalar value to a variable. So in the previous volumes we've frequently seen things such as x is equal to 5, or maybe a is equal to minus 10, where we're assigning values to a scalar variable. Well here, rather than assigning scalar values to a variable, we're assigning a vector to a variable. However, when we're writing a variable that represents a vector, there are actually some notations that we need to be aware of. Different mathematical texts use different notations, but there are three that are frequently used. The first is to write the name of the variable, in this case v, using a bold font. So if the variable is a vector, we use a bold font. If it's just representing a scalar value, we use a normal font. Now that's easy to do in textbooks or on web pages, but it's a little harder for me to do here on the whiteboard where I'm writing these letters by hand, because when you're writing by hand, it's pretty hard to represent a bold font. So another notation, and it's my preferred notation, especially for working on the whiteboard, is that we can denote that this variable is a vector by writing a small line above the vector. So if we saw things such as a, b, d, maybe v, all of these are vectors because they have a small line above them. So that's my preferred notation. That's the second of the three different common notations, and that's simply to have a small line over the letter, and that means it's a vector. A third notation, which is quite similar to this one, is actually to draw a full arrow over the letter. So instead of having just v dash, some notations use v with a small arrow over this. The arrow just being another way of denoting that this variable is a vector. Now this is more commonly used when we're denoting a vector that travels between two vertices on a diagram. For example, if I had some point here which I named as O and some point up here that I named as P, if we had a vector that travels from O to P, this could be written as OP with an arrow, and the arrow is showing us the direction. It's from O to P. Whereas if the vector was travelling in the opposite direction, if the vector was travelling from P down to O, this would more likely be written as PO. Again, because the direction of the vector is from left to right, it's telling us we're going from P and to O. So this is more commonly used when we're referring to a vector as travelling between two vertices on a diagram, because the arrow allows us to explicitly state the direction of the vector. Now once again, these are the three different notations. That's bold, a small line, or maybe an arrow. And my preferred notation is the small line above the name of the vector. But I wanted you to be aware of the other types of notation, so if and when you encounter them, you're going to know that they're all simply referring to vectors. So that's the first thing that we can talk about in terms of how we've written this vector. The other thing I'd like to refer to and talk about is the fact that this particular way that we've written this vector is known as a column vector. Now I'm going to bring up a new whiteboard because I'm very quickly running out of space. But it's known as a column vector. So v is equal to xy. This is a column vector. But why is this a column vector? Well, it's actually quite simple. This is simply called a column vector because we've listed our components of the vector, the values that make up that vector, in terms of a column. They're in a vertical line. And importantly, the first component of the vector is always at the top, and then we travel from top to bottom so that the last component of the vector is always at the bottom. Now this vector only has two components. That means its first is at the top and its second component is at the bottom. But it's a column vector because we're listing them in a vertical column. But equally, vectors can be written in row form. So a row vector for the same vector could be written like this. This would be a row vector. So in row form, we're horizontally representing our components from left to right rather than vertically from top to bottom. Now you'll notice this is quite similar to how we represent coordinates in Cartesian, 2D Cartesian space. But you'll notice, unlike coordinates, there's no comma here separating the two different components. And also, we're using square brackets rather than parentheses. Now, these aren't hard and fast rules, but the lack of commas and the use of square brackets rather than parentheses are generally the convention when writing vectors versus writing coordinates. So almost uniformly in almost all maths texts that I've encountered, coordinates are written with parentheses and a comma, whereas vectors are written with square braces and no comma. Now again, it's not a hard and fast rule, which means you may encounter mathematical texts that write vectors using parentheses or possibly even put commas in between the components of the vector, but in general the convention seems to be that square brackets and no comma is the way to write a vector. So hopefully you'll now understand the differences between a column vector and a row vector, but in actual fact, when we're dealing with vectors alone, these differences are not significant. So it's not something that I'm going to really get into on this DVD into great detail because it's not going to affect us during this DVD. However, in more advanced mathematics, where you start combining vectors with matrices, then the difference between column and row vectors is important. So I wanted to point it out that they can be written in both ways. For what we're doing, and for pretty much all intents and purposes really, they mean the exact same thing. And if you see a vector written in either column form or row form in a textbook, they're both vectors. It's only when we get into more advanced mathematics where we start dealing with matrices rather than just vectors that the form they're written in has an impact. But for what we're doing on this DVD, and for pretty much everything that you're going to be dealing with in terms of vectors alone, column vector and row vector are interchangeable. They're just two different ways of writing the exact same thing, and if you see a vector written in either form, it's just a vector. You know that it has, in this case, two components, and you know the order of the components based on either top to bottom or left to right. So now that we've seen the way that we can write vectors, both in terms of the notation of the variable and how we write the components, let's actually write some vectors using this notation. So we get used to how these vectors might look in terms of their components and how that relates to our Cartesian space, if you will, because so far we've kind of gone over this quite quickly. So let's practice some examples to help this sink in. So I'm going to scroll down to give myself some space on the whiteboard. I'm going to draw another set of, my apologies as Photoshop goes crazy, I'm going to draw another set of Cartesian axes. Fantastic, so there's our x, there's our y. And let's say, for example, that I had some vector that had a magnitude of 20. We've talked about 20 a lot, for example, 20 miles an hour. And I'm going to say that that vector is traveling in the same direction as our x-axis. So let's say, for example, that it went from 0 in x, and we know it's 20 units long, So let's say, for example, that this was 20 in x. We know our origin is 0. This vector is travelling in the same direction as our x-axis, and it's 20 units long. That means we know the components of this vector. If we said this vector was a, we know the components of this vector are equal to 20 in x and 0 in y. How do we know this? Because it's travelling 20 units in x, and it's going nowhere in y. It's travelling 0 units in y. So this is a vector because it's a directed line segment, if you will. I'll get into that a little bit later, but it's a direction as well as a magnitude, a length and a direction. And the components of this vector are telling us how far it's travelling in x and how far it's travelling in y, and we're assigning that vector to a variable that I have just arbitrarily called a. And to denote that this is a vector, I have used one of our three notations. The notation I have chosen is the small line above a. Well, let's say we had some other vector. Let's say I had a vector b, and that vector was equal to, I don't know, let's pick on 10 and minus 5. What would this look like in our Cartesian space? Well, it's a vector that's travelling 10 units in x, and when it's travelled 10 units in x, it's also travelling minus 5 units in y. So we could, if we started our vector at the origin, again I'm going to talk about that a little bit later, but we could travel 10 units in x, and we travel minus 5 units in y, so that's about minus 5 there. So we travel 10 units in x, minus 5 units in y, and we get a vector that would look something like this, and this would be our vector b. So again, it's how far are we travelling in x and how far are we travelling in y, and you're seeing that this is giving us both of the pieces of information that our velocity was still giving us, in terms of the fact that we're getting not only a speed, if you will, a magnitude, which is how far are we travelling, or rather how fast are we travelling, but it's also giving us a direction, because we can see we're travelling, in this case, it's going to be slightly more than 10 units. We'd have to apply Pythagoras' theorem here, and again, this is something we're going to get into in a later video, but we can see we're travelling slightly further than 10 units, and we can see the direction that we are travelling in. And that's very important. A vector, again, is both a length and a direction. In terms of velocity, it's a speed and a direction, but vectors can be used to represent all sorts of different values, as we will see throughout this DVD. So that's another example of a vector. Let's try one final example here. So let's say we had a vector c, and let's say c had the components minus 4 and minus 6. So again, this is telling us we're travelling minus 4 in x, so right around here we could say it was minus 4, and then minus 6 in y, something like this, which would give us a vector that looks something like so. So again, this is our vector c. It has a length and it has a direction, and you can see how the components of a vector, if you will, written in Cartesian form, how they explicitly define our vectors in Cartesian space. So this is very, very useful to us. The notation, if you will, how much movement do we have in x, followed by how much movement do we have in y. It's very useful to us, and it's actually the form that is most commonly associated with vectors in 2D, in 2D Cartesian space. So when people say they have a 2D vector, it's almost certainly going to be expressed in this form. How far are we travelling in x, and how far are we travelling in y? But why is this the most common form? Why is this the form that everyone has adopted and uses when they're talking about vectors? Well, as you're going to see throughout this DVD, by representing vectors with Cartesian coordinates as opposed to, say, using the spherical coordinate system we discussed earlier, or some other way of representing these values, by using Cartesian coordinates we can actually perform a large number of very, very useful operations on those vectors. So vectors are represented using Cartesian coordinates when we're dealing with vectors in Cartesian space. If we're dealing with a vector in 2D Cartesian space, it makes sense that we'd have an x component and a y component to those vectors. That you also notice every time I've been referring to vectors and putting them into our Cartesian space, we've been drawing lines, but I haven't really gone into detail on these lines, but we have seen that we've been drawing lines that represent those vectors? Well, this is actually very common. It's a very common thing to do, and it's incredibly useful. We can represent a vector, a magnitude and a direction, a length and a direction, as what is known technically as a directed line segment. So that's not just a line segment, which would be some section of a line that we know has a length, but it's also a directed line segment because it has a direction. We know which direction are we traveling in, and we know how far we are traveling in. So vectors can be represented as a directed line segment. The length of the line is representing the magnitude of the vector, and we've seen this without even really defining it. We've seen this as we said, oh, we're traveling 20 units in x and 0 units in y, therefore our line here, if it's 20 units long, that's the magnitude. It's the length of the line. It's the magnitude of the vector. So we've seen it indirectly without really defining it, but here I am defining it explicitly. The length of that directed line segment represents the magnitude of the vector. It represents the size of the vector. The direction that the line is pointing in represents the direction of the vector. And the important thing is that vectors will have an arrowhead, because the arrowhead is explicitly telling us that direction. We saw this line here. If I had a similar line, we don't know the direction of this line, because we could be traveling this way, but we could also be traveling this way. You'll notice any line segment actually has two different directions that it could represent. So a vector, when represented as a line segment, must explicitly have an arrowhead. But there are actually two different ways that we frequently draw vectors using these directed line segments. Different textbooks again will take different approaches, but there are two ways that I frequently have seen vectors represented as lines. The first is the way that we've been doing so far, which is to put the arrowhead at the end of the line segment. For example, all of these vectors that we've been drawing here have the arrowhead at the end of the line segment. The second approach is to actually place that arrowhead in the center of the line segment. For example, this vector, or maybe we have a vector like so, or maybe we have a vector like so. They both mean the same thing. In both cases, they're a line segment that has a direction. It tells us which direction of travel we have, and therefore, because we have both the length of the line and the direction, they are still vectors. They're just two different ways of noting vectors. Now, one of the most important things to realize when representing vectors in this way as lines in 2D Cartesian space is that these vectors are free to float around in Cartesian space. So allow me to scroll down to explain this further. I'm going to draw yet another set of Cartesian axes. So we have our x-axis, we have our y-axis. And let's say we have some vector, and I don't know, let's say we have the vector d, which is equal to 4 in x and 2 in y. What do we know about this vector? Well, we know this vector has a direction, and we also know it has a length, but we have no restraint on where this vector starts and ends in our Cartesian space. This doesn't tell us anything about where this vector starts and ends. It simply tells us how far we travel on x and how far we travel in y. And that means this vector could be drawn anywhere in our 2D Cartesian space. For example, we could start here and we could say, okay, we travel 4 units in x, 2 units in y. So this is our vector d. But we could also start here and travel the same amount. We could start down here and travel the same amount. Now, all of these, my drawing's a little bit off, but all of these should be the exact same direction and the exact same length. But the important thing is it's free to float about our Cartesian space. Nothing locks it in place because of the fact that all we know in terms of the components of our vector is the direction and the length. It has nothing to do with its position in Cartesian space, and that is really, really important to understand, that a vector is free to float in Cartesian space, and all of these vectors, which I should have noted were vectors, all of these vectors are the same vector. They're all d, because you'll notice they have the same length of line and they have the same direction. So they have the same direction, the same magnitude, and because of that, they are the same vector. So when we're talking about the components of a vector, two vectors are equal when their components are identical. So we know the components of each of these vectors is 4, 2. This guy would be 4, 2. And this guy also is 4, 2. And because the components are equal, because their direction and magnitude is equal, they are the same vector. So we could write this in generic form. We could say if we have two vectors, for example, a vector A which is equal to x1, y1, and a vector B which is equal to x2, y2, then we can say that these vectors are equal. So A is equal to B only if x1 is equal to x2 and y1 is equal to y2. And that's the same with any vector, no matter how many components you have. Those vectors are only equal if the same components are equal. That is to say, the first component of vector 1 is equal to the first component of vector 2, and so on. So in the case of our 2D vector, x1 must equal x2 and y1 must equal y2. And we've seen this here where we have these three vectors. Because all of these three vectors travel 4 units in x, that means all of the x components of the vectors are equal. And because they all travel 2 units in y, all of the y components of those vectors are equal. Therefore, because all the x components are equal and because all the y components are equal, they have the same length, they have the same direction, they are the same vector. They are all vector D. Okay, so to recap, we have seen quite a lot in this video. It's been quite condensed, but we have actually seen quite a lot. The first thing we saw is that a vector is simply a collection of numbers. Now in 2D Cartesian space, this almost always means a distance travelled in x followed by a distance travelled in y. How far are we travelling in x? How far are we travelling in y? And that's telling us not only the direction, but also the length, the magnitude of that vector. And we've seen that this can be written in two forms, either as a column vector in the form v is equal to x, y, or as a row vector, v is equal to x, y. We've seen that the variable names here can be written either in bold with a small line above like I've got here, or with an arrow above. All the same, well, all different notations, but they all mean the same thing. They all mean we have a vector. We've discussed how vectors can be represented graphically as directed line segments. That's a line that has a length and a direction denoted by the arrowhead. And the most important thing to remember, again, is that a vector is free to float in Cartesian space. It's not locked to any one position because it represents a magnitude and a direction and nothing else. Nothing in the components of the vector tell us anything to do with the position of that vector. It's free to float around in Cartesian space. And finally, we took a very brief look at vector equality. And there's really nothing to vector equality. As long as the components are the same, we have the same vector, and that's really all there is to it. So I just wanted to cover it quickly in this video since it sort of related to what I was doing with drawing D in different places in Cartesian space, rather than give it a video on its own. It would have simply taken 30 seconds and not really been a very productive video. So in the next video, since we've wrapped up everything here, we are going to continue our look into 2D vectors. We're going to see how we can add and subtract 2D vectors and what this means in terms of their graphical representation. But that is going to conclude everything that I wanted to cover in this video. Thanks a lot for watching, everyone.